Sometimes we encounter a situation where we have two identical Lewis structures, but the placement of something like a double bond can be placed in more than one position and still yield the same Lewis structure. This is a situation known as resonance. What happens in resonance is a double bond that can be placed in more than one location is free to move about several locations as long as the Lewis structure indicates that the double bond is allowed to go there and results in a valid structure. Ozone is an example of a molecule that has resonance. In the Lewis structure you see here, there's a double bond on the left and a single bond on the right. But realistically, this double bond could be on either side, with the single bond opposing its position. The reality of the matter is that ozone happens to spread its double bond out across both oxygens, creating this resonance structure. And we see this when we look at ozone because we find that there's only one bond length between the oxygen atoms in ozone. That is, they have 1.28 angstroms bond length, which is 0.0128 nanometers, so it's pretty small. But the nice thing about resonance is it helps deal with things like formal charge when we can't get away from having to put a formal charge on an atom. So resonance actually helps stabilize and helps us keep molecules together because these electrons are free to move back and forth between the two areas, the two atoms, and so they spread out the charge. It's kind of like the atomic equivalent of hot potato. They're constantly being jumped between positions. And so what we result with is a situation where we have electrons which are said to be delocalized. That is, they're free to move between places rather than just being stuck between two atoms. So what you could see here is that in the resonance structure, we can have an oxygen with a double bond here and a single bond here, or we could just have the double bond there and the single bond there. Notice again, it doesn't change the overall structure. Both Lewis structures are just as correct, but the double bond is free to move between the two oxygens. And so when we have electrons that are in a resonance structure and they're free to move around, we say they are delocalized. That is, they are not localized between two atoms. They are free to move around two or more atoms. And resonance is a very common thing you encounter, especially in organic chemistry. Organic chemists love to talk about resonance, and especially this molecule right here, benzene. Benzene's a six-membered carbon ring that makes essentially a circle, and it has alternating single and double bonds, meaning that the electrons on the carbon atoms are free to move around wherever they want to as long as they're moving between carbon atoms. Now, if this doesn't quite gel with you, that's okay. I recommend you check out some of the problem-solving videos immediately after this video when you can go and watch and see how Lewis structures are drawn and some situations where resonance might be possible. There are some other things you need to keep in mind when you are working on Lewis structures, and those are exceptions to the octet rule. Remember, the octet rule says all atoms are trying to get 8 electrons around them. That's what's driving the formation of chemical bonds. But there are some exceptions. The first one being hydrogen. Hydrogen only has one valence electron, but it only wants 2. If you remember the electron configuration for hydrogen, it was 1s1. And as you recall from our atomic orbitals, we know s orbitals at most can hold 2 electrons. So that's why hydrogen is always wanting 2 electrons rather than 8. Also means hydrogen is never a central atom when we draw a Lewis structure. Boron and aluminum are also a little strange. They have 3 valence electrons, and yet they only want 6 rather than 8. And the reason they want 6 is well beyond the scope of this class, but bear in mind this will be something you need to pay attention to when you're drawing Lewis structures involving boron and aluminum. Consider the molecule boron trifluoride. If we try and draw the Lewis structure for boron trifluoride, giving boron 8 electrons, what we find is we always end up with a structure with formal charges. But because boron is okay only having 6 electrons around it, what we find is that the dominant form of boron trifluoride is simply a boron connected to 3 fluorine atoms with a single bond here, the single line, as opposed to a double bond here, which ultimately forces a formal charge on boron and the fluorine atoms. So when it comes time to dealing with these boron and aluminums, just remember that it's okay to have less than 8 electrons on both boron and aluminum and not worry about the octet rule, because it's more important to keep those formal charges as small or as close to 0 as possible.